Well, hello there. We're going to be talking some more about exponential functions, exponential growth, exponential decay, percent decrease, increase, things like that. Some more applications of exponential functions. Let's get into it. So we have the graph of an exponential function. F has a y-intercept, y equals 12, passes through the point 136. Write an equation for f of x. So just think about what we need to know if we're going to write the equation of a exponential function. We want to know, it's like something like f of x equals a times b to the x. And so we've got our starting value, our y-intercept when x is 0, and then we have our growth rate, decay rate, here. Remember, so just think about what I just said. Our y-intercept 12 is, we know that point, 0, 12. Okay. So we've got that down, and so then we need that rate of change. So we have these 2 points, 0, 12, and 0, 30, or 136. And so we want to look at, what are we multiplying by? What number are we multiplying 12 by to get to 36, right? So of course that's 3. So that's that's our growth rate, right? We always take that later one divided by the earlier one, and so 3. There's our b value. So there we go. That's what we needed to know. So f of x equals starting point, starting value, y-intercept times growth rate, all to the x power. And then just remember, we cannot say that's equal to 36 to the x. Can't multiply those. Easy peasy. Next one, so the population of a small town in Michigan, Y, is 14,500 people at the start of 2010. Each year the population increases by approximately 3.5 of the previous year's population. Write an equation modeling the town's population T years after 2010. So one thing I'm seeing, is here this, percent increase, right? So we talked about that. We take the 100% that we already had, plus 3.5%, right? And so writing that as a decimal is 1.035, or we use 1 plus 0.035 as our growth rate. Another thing I'm seeing here is this idea they want us to have like kind of a new year 0, this T years after 2010. So we talked about this in class, like how to make that work, but that'll be some little stuff going on the exponent. And the other thing I see here is, is our starting value. So the population is y, so y equals, instead of something like p of t or something like that, it's just y equals. So our 14,500, small town, times 1 plus, so the 100% that we have, plus 3 point, about put 35, so it should be 0.035, very common mistake. And then T years after 2010, so that way we deal with that, like if I said, how many people would be in 2015, we'd have to take the 2015 minus 2010. So what we do is we go ahead and put that into the problem. We take T, get a color here, T minus, good Lord, struggling here, 2010 in the exponent. So just watching your handwriting, right, that needs to be small and up there in the exponent spot. So there'd be our function. Again, so if we just want to plug in certain years, so again, what this allows us to do is just plug the year in straight. So if I just want to plug in, 2020, just plug that right in there. It'll do the subtraction for me, and take care of all that. So too shabby. Let's see. Table below represents an exponential function g. Write an equation for g of x. So like we just talked about earlier, we need the starting value and we need the growth rate. So what I can tell from a table is, that growth rate's pretty easy to find. So basically the idea, like, what am I multiplying 25 by to get to 20? All right, what am I multiplying 20 by to get to 16? So remember when you're doing that, trying to figure that out, you always want to take the later term, in this case 20, and divide by the earlier one, 25. Or or if I could take 16 divided by 20, or I could take 12.8 and divide it by 16. So you want sequential ones, right? Consecutive ones. But you also always want to take the later one divided by the earlier one, the later one divided by the earlier one, later one divided by the earlier one. So checking all these would just make sure that we have the right value, that these all should be the same. So 20 divided by 25, it's 4/5, which is 0.8. 16 divided by 20 is also 4/5, which is 0.8. And I would assume that 12.8 divided by 16 is also going to be 0.8. Check that real quick. And it is. So there's my growth rate, or I guess in this case, decay rate. So I'm only keeping, each value is 80% of what it was before. We're not losing 80%, we're keeping 80%. And I need a starting point. So remember, our starting point is when x is 0, right, our y-intercept. So I can't use, it's not always the first value in the table. So in this case, I need to figure out, what was going on here, right? What if x was 0, right? That's what I know, right? I know when x is 1, 2, 3, 4, 5, but I don't know when x is 0. That's the number I need when x is 0. So I need to go this direction, right? So to go this direction, we were multiplying by 0.8. So I need to divide 25 by 0.8. So 25 divided by 0.8. Right, remember, you divide by a small number, you should get a bigger number. I got 31.25. So there's my starting value. So g of x equals, so 31.25 times my growth rate, or decay rate in this case, was 0.8. And that should be to the x power. There we go. Definitely something you guys should be able to do. Another word problem. Department store currently has approximately 320 shoppers a week, but this number is decreasing by about 2.7 each week. Write a function s, the model's the number of shoppers as a function of weeks. So shoppers as a function of weeks. So starting value, right? This percent decrease idea, so from 100%. So 100 minus 2.7. You can do that math, or you can just write it as 1 minus 0.027 in your function. So S of W equals starting value 320 times 1 minus 0.027 to the W power. So my input here should always be my variable here. Shouldn't put x there. W. There we go. Table of values is given for the number of site users. A new website has T weeks after its launch. So number of people at the site as a function of time. Assuming the growth is linear, complete the table. So linear growth, we're repeatedly adding something over and over again. So just thinking like 24 plus something. So plus, I'll call it x. It's going to get that, and then that, whatever that number is, plus so that same number is 186. So one way to think about it here would be like 24 plus x is 186. Another way to think about it is, we know it's a line, right? Y equals mx plus b. Right. B is our starting value, which is when the y-intercept when 24. So 24 would go there. Mx. So m is the slope. M is the thing that we're adding over and over again. So I kind of messed that up here as far as my letters go. Let me change that. So the thing that we add over and over again when we talk about lines is the slope. Like that's our change. So I'm gonna go ahead and rewrite that as plus m, just to make it more consistent with things that we've talked about in the past. So that's what we don't know, right? We don't know that value. So if we're looking for that, we have to know the other two things. So I need to know where we end up, which is what the 186 is. So 186 equals, and then m, which we don't know, times x. I have to know x, right? X is the number of steps, right? Right over there, right? X is 2. Right? Start at 0, took 2 steps, so x is 2. So m times 2. So if you notice, these equations are actually the same. Right? 186 equals, of course that's on the other side, 24 is on, switch sides, but it's just the sides of the equations. But, m times 2, m plus m, these are the same thing. 2m's plus 24, 2m's plus 24, the exact same equation. Okay? So I'm just going to go ahead and solve the first one. So minus 24 from both sides. So I get 1, let's see, 62 equals 2m's, and divide by 2. So m is 81. So write a linear model for S of t. S of t. I need my slope, which we just found our change. We're changing by 81 each time. Times t, not m. Or sorry, not x. We have t's in this problem, not x's. And then plus our starting value, which was 24. Our y-intercept. So there's the linear function if it was linear. Assuming the growth is exponential, complete the table. So what's there's exponential growth and linear growth, right? Exponential means we're multiplying by some number, right? And that's the growth rates we're multiplying, and we call the growth rate b. I'm going to use the right letter this time. So that times b would be that, and whatever that number is, and that number times b again would be 186. So again, we kind of think about this in two different ways. So kind of here, just in looking at this way, that we take 24 and we multiply it by b, and we multiply it by b again, and that gives us 186. There's one way to think about it. The other way to think about it would be saying, like, what's an exponential function look like, right? Like y equals a times b to the x. So b is the thing we don't know. We don't know what we're multiplying by, but we know where we're starting, right? Our starting value, the 24. We know where we're ending up. That's the y. That's the 186. We don't know what we're multiplying by, but we do know how many times we're multiplying, right? What's our x value, right? The difference here is 2, so our x value is 2. So are these the same equation, right? 186, 24 times b times b. Well, it's b times b. B times b is b squared. 24 times b squared. So again, they're the same equation. Okay? It's just two different ways of thinking about how to set it up. But we end up in the same place. Okay? So let's solve this one, right? Because it's the simpler one. So of course we, SAD maps, we're going to divide by 24 first. 186 divided by 24. Don't know that one off the top of my head. It's probably, no, it's not 4. 7.75. So 7.75 equals b squared. And then I get rid of the square by square rooting. So the square root of 7.75. 2.783, blah, blah, blah. So 2.783. 88 equals b. Normally when we square root, we do a plus minus. I know the growth rate can't be negative, so I'm not going to bother writing it down. Mathematically, there's another answer there, but the growth rate has to be positive. Even if it's less than 1, it's still positive. B is never negative. So just knowing that, I'm not going to bother writing it. And I'll probably just round that to the nearest, I'll say thousandths, so I'm going to say 2784. It doesn't tell us what to round to, so I'm just going to go ahead and say that. So writing our model, S of t, starting value, which was 24, times 2.784 to the t power. All right, that is that. Hope you have a wonderful day.